Hello, so today I'm going to be doing a showcase and an explanation of my 5 Hz Minecraft Redstone computer. So we're going to start off with a little program and then I'll do some explaining onto how I can make this work so fast. So it's not completely finished yet. I still need to do conditional statements. So while it will do the additions and display them onto the screen, it's not going to stop once it gets to I think it's 233 is the highest number for 8-bit. So yeah, it is pipeline, so it does take a little bit to start up, but then it gets really fast. Yep, and then it's just not going to stop because there's no conditional statements. But yeah, it is still pretty fast. So now I'm going to go into what makes this so fast. So there are 3 things I would say that make this really fast. One, this is a pipeline computer. If you don't know what that is, that's basically where instead of sending out one instruction, waiting for it to calculate, and then sending out the next one and waiting for it to calculate, I'll send out the first instruction, and then before it even finishes, I'll send out the next one, and the next one, and the next one, and the next one, and the next one. If this computer wasn't a pipeline computer, it would be about 1 Hertz. So it's still a fast computer on its own, but pipeline just makes it that much more fast. Another thing is it's not very laggy. There are a few things I did to keep it that way. For example, on the program memory decoder, there's no decoder here because running a 7-bit decoder at 5 Hertz was super laggy. So I just opted for a timing-based design. And I'll talk about that more later when I talk about jumps and stuff. And then the third thing is just overall consciousness of every repeater you place. Every repeater in here is needed. There's no unnecessary ones, and if I thought that maybe there was a way I could remove a repeater, I would try for hours to remove one repeater just to lower it by 1 tick. Because when your instructions are 2 ticks long, every single tick hurts you really bad. So most repeaters, we can see here, are powered by either signal strength 2 or signal strength 1. Let's see. That one's powered by signal strength 2 too. Guess I got a little bit of optimization to do. But most of them are powered by signal strength 1. And that just keeps the total time from one side of the computer to the other super short. So I guess I'll talk about the jumps next. So as I was saying, it's a timing-based design, so every 2 ticks it will send out another instruction or another line of code. There might not be an instruction on that line, but it will send out a new line of code. But the problem with this is that there's no way to stop this. Or, well, there is, but you wouldn't think there would be, because there's no repeaters here. I mean, there's no pistons here to cut off the signals. There's no real any way to stop this except for these locking repeaters. So these repeaters lock these repeaters. And I just use some very careful timing to have the right repeater locked at the right moment to stop the signal. So when I actually start up the computer, this is the start line, it will also send a signal down here and start up this clock. And this clock is perfectly offset and perfectly timed with the start of the computer, so that when I run a jump instruction, it will turn this line on, or off I guess, and it will retract these pistons for exactly 2 ticks. And then one of these 2 lines will turn on, and then we have the odd. So this one has every other, and then this one is every other. So they're staggered. And then that just makes it so that when, for example, let's say that the signal's right here, and the power from the bottom reaches up here, this repeater would be locked, and this repeater would be locked. and then the signal just kind of goes away. Because if this is powered and this is locked, there's nowhere for the signal to continue on to. So that's why to stop the signals. How I start a new one, there's two decoders here. There's an X decoder and a Y decoder, and they'll kind of just meet in the middle with an AND gate, and then one of these 128 torches will turn on depending on the data you send to the decoder, and that's how you start a new signal. So for a jump, you would first stop it, and then you would start a new one. This makes it really easy to do interrupts because that clock is always perfectly timed. So whenever I want to stop the computer, I can just flick or de-extend and extend the pistons real quick, and it will stop the computer. So that makes me want to go with an interrupt design. I haven't quite figured that part out yet. I'm still figuring out some designs I could do before I actually build them. But yeah, that's jumps and how I'll do conditions when I get to it. Next, I'll talk about the instruction set. So there are 3 parts to this instruction set. It's a pretty small one in general. There's only data, location code, and opcode. So the data can either be a number, it can be an address. Mostly it's going to be a 4-bit address because most addresses in this computer are 4 bits. I've only got 16 bytes of RAM, so it's a little small, but you probably could extend it if you wanted to, but I just went with 16 bytes. So it can be either a number or an address. And then location code, I'm going to talk about buses before I talk about location code though. There's 6 buses. There's the main bus, which branches right off from program memory, and then goes along the bottom line here. This is also the main output for the cache or the dual read RAM. And then it branches right here. It goes into the bottom input of the ALU, or it goes up here and goes into the input of the caches. Then you got the secondary bus, which, like the main bus, is the secondary output for dual read RAM. It just goes into the other input of the ALU, nothing too special. Then we got the first auxiliary bus, which starts right here, branches off from the main bus, and then just goes into the main decoder for cache. And then the secondary auxiliary bus starts here and goes into the secondary decoder for cache. And then we have the jump bus, which also branches off from the main bus right here and just goes a little bit lower than the secondary auxiliary bus. And then this just decodes where you want to send your location in a move command. I'll talk more about move commands in a little bit, but this just tells you where are you going to send that data. And then we have the jump bus, which just takes the data from the main bus, branches it down here, and sends that to the jump decoders. And that's how you start a new location. So now I've talked about that, we have location code. So the location code is basically describing what buses you're going to have open and which ones you're going to have closed at any given instruction. So if you put in 0, 0, it will open up the main bus and close off all the other buses. And that would be used if you wanted to save a value into cache, if you wanted to save a value into RAM, if you wanted to save a value into a display register, and if you wanted to save a value into RAM address registers. And then we've got 1, 0, which is referring to an ALU operation. You'll use that every time you're dealing with the ALU. It closes off the main bus, opens up the first and the second auxiliary bus, and then closes off all the other buses. So if you think about it, it has the main and the secondary cache decoders. So depending on what address you put in those, a value will be on the main bus and on the secondary bus. And then those both get perfectly timed and get put into the ALU. And then depending on your opcode, it can do different ALU operations. And then also it will get calculated first, and then depending on your opcode as well, it can be either saved into register A or register B. So a lot of different functionalities with the ALU. Then we've got our location code 01, which is the move location code. So that will basically open up the first and the move bus and it will shut off every other bus. And that basically, first of all, it will put a value onto the main bus. It will be decoded. A value from cache will be put onto the main bus. And then, depending on what you put onto the move bus, depends on where that data will end up. So you've got a certain amount, you've got certain registers that you can load data from and certain registers you can load data to. So the registers you can load data from are register A, register B, register C, register D. You've got the two human inputs. Those are the ones that you'll input from the control panel. Then you've got the random number generator, and you've got the RAM out register. That's just the register that when you load a value from RAM, that's where it will end up. And then the registers you can save to are the display registers. You can also save to the four main registers, register A, B, C, and D. And then you can also save back to RAM, or you can save to a RAM address register. I'm thinking about making it so you can save to the jump address registers when I implement them, but I'm not quite sure I'm going to be able to do that. So we'll see how that goes. And then you've also got location code 11, which I don't think I'm ever going to use. It basically just turns off all the buses. Don't see really a point to it, but it's there. So yeah, that's location code, and then you've got opcode. I split it into two parts just for simplicity. There's the section code, and then there's the opcode. So the section code is dealing with what location in the computer or what section of the computer are you dealing with. Depends, like, are you dealing with the ALU, the cache, the jump registers, the RAM, telling the computer what part you're dealing with. And then the actual opcode is what do you want to do in that section. So for example, the opcode of 100 with the section code of 010, it's basically saying save to register A. So save whatever value is in data to register A. Some other examples are opcode of 001 and a section code of 100. That basically says add and save to register B. So you're going to add whatever in the cache at location 1, and you're going to add whatever in the cache at location 2, and you're going to save that to register B. And similarly with this one's add and save to register A. So yeah, there's lots of ways you can do that. When I finish the computer and I implement all the conditional stuff and I finish up RAM and I make a control panel and do all that, I'll be making another video going over those parts and also showing you how to program this and then showing a list of all the opcodes and how you program it. There's also some tips and tricks that can save time in programs. So yeah, I'll be doing that when I finish. Let's go over some of the actual parts now. So most of the components of this computer were designed by me. There's one exception, I'll talk about it later. So this is the dual read RAM, or the cache. There's 6 bytes here. It's 1 tick read, 0 tick write. Or I guess, yeah, 1 tick read, 0 tick write. So it takes 1 tick to read a value, and it takes 1 tick to load a value out. It's staggered for a kind of a weird reason. It's staggered because the ALU has to be staggered, and the actual distance it took to unstagger the ALU and then put it into the cache took about another tick, and I don't really have a tick to spare, so I just designed a staggered version. I actually have an unstaggered version right here, which is basically the same design. This one's a little shorter because staggering it makes it a little more complicated in some cases and a little less complicated in others, but it ended up being a little bit longer. So there's the dual read RAM. Now we've got the ALU. So this is a 4-tick ALU. It's a carry cancel adder with a inverter at the beginning. It can only do addition and subtraction right now. I'm looking into being able to do more, but I haven't really seen a purpose for it right now. I know there are purposes for it, but I don't really want to mess with that right now. This took me 5 months to design, so kind of taking a break from ALUs right now. It uses a one-tick XOR gate I designed, which is continuous. It also has to be staggered, but the reason the ALU has to be staggered is because of these one-tick or zero-tick diodes, which basically allow data to go one direction but not back. And that's how the carry cancel part of the adder works. So yeah, that's the ALU. And then we got RAM. So this is a zero-tick read, zero-tick write RAM. So it's a little bit faster. It's also my design. It uses bud power saving, and then it uses this weird system where both of these load lines have to be turned off before it actually loads the value from that location. So I just use the new target blocks, which have saved me in so many instances, but yeah, that's how that works. And then we also have the BCD converter. That is the only part that I have not designed, and I've tried so hard to get it either smaller or faster, but it's just, I don't really see a way to do it. The person who designed this is NeoMaster, so I'll put a link in the description if you want to go check his video out. He does a really good job of explaining how BCD converters work and then how to build this one. And then I just have a kind of normal BCD to decimal or 7-segment display decoder. It is timed a little bit differently because I was having issues with the numbers actually disappearing before they fully appeared, so that was a little bit of a problem. It made it really hard to read the screen. So you might have noticed that the numbers came on all at once instead of staggered. Yeah, that's just because I spent a little extra time timing every part of this. I think that's about it. I guess I can talk about this. So the opcode, or I guess the instruction bus, it looks a little different than most computers. I don't decode everything in one big block and then bus all the control lines to where they're needed. That, first of all, is a little bit more laggy, and it doesn't allow for multiple instructions to be decoded at once. So I just went with the design of decode when I need to decode. So I'll only decode something when I'm like at the actual place where I need that control line, and that just saves on space and a bunch of other things. Actually I'm gonna break down this Fibonacci program because it works a little bit differently than most do. There's only 4 instructions in the entire program, and it will stay 4 even when I finish conditional statements. But the first one is just load 1 into register A. That's pretty self-explanatory, but you got to start with some value, so I just started with 1. The next one, it starts the jump, or it starts the loop, I guess I should say, the continuous loop, because there's no conditional statements, but basically this is saying jump, this is my jump command, and then I'm saying jump to position 2, so it just jumps back to itself. Next I have an addition, so this adds register A and register B. There's nothing in register B right now, so it just adds 1 and 0 and saves 1 to register B. So now we have 1 in register A and 1 in register B. And then another thing I need to say is I have a little thing here that makes it a little more efficient. So I have a setting that you can change in program that basically says save every value coming out of the ALU to the display. So if that's turned on, when you do an addition, the result will automatically be displayed to the display. You don't need to move it to the display. It will just automatically go there. So that's how I am able to do this really in 4 instructions. And then we have a little bit of a problem. You'll see these 3 instructions that are never used. That is because it's a pipeline computer. So you might think about it. So when I load the values from when I load 1 from A and 0 from B to have them added together, it's going to take at least 4 ticks because the ALU is 4 ticks. I think it takes a total of 7 ticks, maybe 6.5. I haven't quite figured that out. It's a little finicky, but it takes a little bit of time for that value to be added and then saved back into register B. So I have to wait for the result from this calculation to be saved into register B before I can send out the new calculation. Because or else I would add 0 and 1 together twice in a row because the 1 wouldn't be saved to B yet. So that's a little bit of a problem. It's not a problem for most instructions. For example, you can save to register A and register B right after each other. There are just a few specific instructions that require a little bit more time. But yeah, that's why that's like that. It doesn't really slow it down. I mean, if I put these two additions right next to each other, it still takes a little bit of time for the jump to execute. I'm actually going to show that because this is one of the tips to make it faster. When I start this jump, it doesn't halt immediately. There's no way I could get this signal down there decoded, release those pistons, and put the signal back up here to stop the computer in 2 ticks. That's impossible. It takes about 6 ticks, probably a little longer. But you'll see this is the actual instruction that it gets decoded on, or that the jump is loaded, and it actually ends up halting right here. So that's one of the ways I can do it, or I can make this faster, is because I know I need to jump. So I'm just going to start the jump back here, when I really want it to stop right here, because I need to do these 2 additions. So even though it takes a little bit of time for the jump to be decoded and executed, I'm still not wasting any time. So I'm actually going to run the computer right now. Got to fix a few things here. So you'll see this second instruction is where the jump is declared, I guess, and then it stops a little bit later. Oh, the heck. That was stupid. I forgot I don't have a observer here, I guess. Come on. Remove that observer. Don't know why I did that. Okay, clock is off. Everything should be good. Let's start. So you can see it stopped over there. And you can see those repeaters firing. But it actually, in a perfect world, it would stop right here, but it stops way over there. Just because the time it takes for that instruction to go down and get decoded and come back up to the execute phase. So if we just stop the computer. So that's one of the problems I'm having with this being a pipeline computer. Of course, pipeline makes it so much faster, but it does introduce some problems. But I think it's still way faster with pipeline than without pipeline. So yeah, that's about it. If you have any questions, feel free to put them in the comments below, and I'll be doing another video when I actually finish this, and there will be a world download in that video. I don't really see a point in putting a world download in this video because, well, it's not really working. So thanks for watching, and I'll see you later.